Transistors in modern digital circuits, for the most part, do not obey the ideal IV characteristics, or otherwise known as the long channel IV characteristics that was explained in the previous video. There are several effects, commonly known as the non-ideal IV effects or short channel effects, that are modified, and these effects primarily arise from the shrinking of the transistor dimensions over the last 2 decades. So advances in fabrication technology, as a result of these advances, in the last 20 years, the transistor length, the oxide thickness, as well as the width of the transistors, the MOSFETs, have been decreasing. And the reason for decreasing these geometrical dimensions, this is known as scaling, transistor scaling, is so that one could actually get significantly faster transistors that operate at lower power for free. Because just by reducing the size of the W, the L, and the TOX, the transistors would operate faster and consume less energy at the same time. In the 80s and 90s, 10 or 1 micron gate lengths, transistor lengths, channel lengths were common, and today this has dropped down to roughly around 10 nanometers. And you can see this is anywhere from a factor of 100 to a factor of 1,000. Okay, and as a result of these changes in transistor length, okay, so now you've got a really short transistor with a really short channel length. Okay, here you go. We see that any electric field or voltages applied in the drain and source begin to influence the electrostatic properties of the channel. And besides that, we also see that the electric fields experienced by the free carriers in the channel are also much higher now than they were 10-20 years ago. As you know, voltage is equals to electric field divided by length, and there are two voltages of interest to us here. That is the gate voltage, that is the voltage from the gate to the channel. This gives rise to an E field operating over the oxide thickness, and the voltage from the drain to source gives rise to an E field operating across the length of the channel. And the high electric fields in both the lateral as well as in the perpendicular direction modify, influence the mobility, influence the motion of free carriers in the channel, and this has effects on the current. Now these effects are actually termed mobility degradation and velocity saturation. Mobility degradation arises from the perpendicular electric field that is generated by VGS. Okay, and the way and what happens is this electric field actually tends to push free carriers towards the surface, the oxide surface here of the channel, and this increases the scattering of the free carriers, which then in turn reduces the mobility of the free carriers. And this is modeled by a corresponding reduction in the mobility. Basically, this is we now have an effective mobility that is correspondingly reduced and depends on the gate to source voltage, the magnitude of the gate to source voltage. So if you have a higher VGS, the mobility degradation is greater, as well as the threshold voltage. Typically, this function f here is some polynomial relationship with VGS and VTH, and with some non-integer factor. There are several slightly different models, but the important point here is the mobility degradation can be represented by a reduced effective mobility. The second effect is a velocity saturation effect, which arises from E fields applied in the drain to source direction. So an E field applied in along the lateral dimension of the channel impedes motion of the free carriers across the channel, because as the E field increases, the velocity increases, and there will be more impact, more scattering of the electrons or the free carriers as they progress across the channel, and this gives rise to increased phonon scattering. Now, the corresponding reduction in velocity of the free carriers is dependent on VDS, and is captured by this factor right here. Okay, this factor right here, where there is some specific value of E field above which there can be no further increase in the velocity of the free carriers. This is known as the critical E field, and the critical E field causes the velocity of the free carriers, in this case the electrons, to saturate. So any further increases in VDS, that is, which will generate an E field above the critical E field, will not change the velocity of the free electrons. Okay, so this is a parameter. The velocity, the saturation velocity, and the critical E field is a parameter of the device of the material. Okay, and the important thing to note in how we revise the model, the current voltage model. The current voltage model of such short channel devices in the linear regime, when VDS does not exceed E critical, does not exceed some saturation value, VDS set, the magnitude of the current is correspondingly reduced by both the velocity saturation term here and the degradation of the mobility here. But in the domain where VDS exceeds some saturation voltage, okay, the current, and this tends to be in the saturation region of operation of the MOSFET, the velocity is now saturated, and the current is now a linear function of VGT, that is the gate to source voltage minus the threshold voltage. The saturation voltage, the voltage across VDS that leads to saturation, is given by the parallel combination of VGT plus the critical voltage. Okay, and VGT is none other than VGS minus VTH. And so to get a better, a visual perspective of what happens, we have this graph here that shows the IV characteristics. So the characteristics plotted in black are the ideal or long channel IV characteristics of the MOSFET, and the characteristics plotted in blue, the curves plotted in blue, are the short channel IV characteristics that arise due to the effects of velocity saturation and mobility degradation. You can see that the magnitude of the current is significantly decreased as such. Okay, that's the first step. And second, you'd observe that the point where the transistor transitions from linear to saturation, meaning the formation of the channel in pinch and then pinch off happens, this is now a linear function. Oops, let me redraw that. Okay, this is now a linear function of VGT, whereas in the ideal, in the long channel model, the saturation point is actually a quadratic function of VGS. And then the third difference that you may have observed is the current in saturation for these short channel devices are no longer constant. Okay. Current does increase with increasing VDS, and this is due to an effect known as channel length modulation. What essentially happens is this drain, N plus well drain here, forms a reverse bias PN junction with the substrate. Okay, and VD is some large positive voltage, and as the voltage on VD goes up, okay, this is and it saturates the depletion region. The depletion region, as a result of the reverse bias between this N well and the P substrate, actually extends. And when the depletion region extends, it actually pinches off the channel much more. So you see an effective shortening of the channel due to the expansion of the depletion region. And as you may know, a reduction in transistor effective length leads to an increase in current, and this increase is reflected in this very shallow slope here. And the way we model the effect of channel length modulation is by introducing this additional factor, where VA, or the early voltage, is the voltage where, if we were to extrapolate from all the linear points, the points which all these curves at different VG, all these linear lines at different VG intersect the x-axis, will be the early voltage.